There is a highway in western China where the road doesn't climb over the mountains, goes straight through them, for more than 22 kilometers. And at its deepest point, there is more than 1,100 meters of mountain above the tunnel. That's over a kilometer of solid rock between the road and the sky. But the strange part isn't how deep the tunnel is. It's what the engineers had to deal with while putting it there. The Tianshan Shengli Tunnel cuts through the central Tianshan Mountains in Xinjiang, a region where high altitude, extreme cold, strong seismic activity, high ground stress, groundwater, and complex geology all come together. The tunnel crosses 16 geological fault zones. And that means the mountain wasn't going to behave the same way all the way through. Solid rock could suddenly become fractured. Dry ground could give way to water. Stable sections could be followed by areas where the surrounding rock was under enormous stress. So the real question isn't simply, how do you dig a 22-kilometer tunnel? It's this: how do you keep control of a mountain while removing part of it from the inside? The answer begins with geography. The Tianshan Mountains stretch roughly 2,500 kilometers across Central Asia and form a major natural barrier through Xinjiang. For the highway connecting northern and southern parts of the region, engineers had two basic choices: make the road climb around the mountains, or make the road go through them. They chose the second. The Tianshan Shengli Tunnel became the centerpiece of the 324.7-kilometer G0711 Urumqi-Yuli Expressway, which opened to traffic in December 2025 after more than 5 years of construction and an investment of about 46.7 billion yuan. The tunnel itself, at 22.13 kilometers, became the world's longest expressway tunnel. But building it was never going to be a normal tunnel project. A conventional approach would have meant excavating from the two ends and slowly pushing deeper into the mountain. At this scale, that could take years longer than the project could tolerate. So the engineers changed the question. Instead of asking how to dig one enormous tunnel faster, they asked how to turn one enormous construction site into many smaller ones. And that led to one of the most important ideas in the entire project: 3 tunnels. For shaft. The 2 outer tunnels would become the highway's traffic tubes. Between them, engineers added a third tunnel, a central service tunnel. Then they drove 4 enormous vertical shafts down from the mountain above. The idea was simple: don't make the mountain smaller. Make the construction site bigger. The central tunnel created additional access and working fronts. The shafts connected the underground works with the surface and helped solve ventilation and construction logistics. One of them reached roughly 706 to 707 meters deep. Now the crews weren't limited to working from the 2 ends. They could reach the mountain from inside. And that changed everything. The central tunnel would be excavated using hard rock tunnel boring machines, while the 2 main highway tunnels would primarily use drilling and blasting. 2 very different methods. One coordinated strategy. And one machine in particular would become part of the story. They called it Shengli, victory. But the name wasn't the important part. What mattered was where this machine had to go. Into a mountain where the geology could change without warning. Into a tunnel more than a kilometer beneath the surface. And into an environment where cold, altitude, pressure, water, and seismic conditions could all become problems at the same time. The mountain wasn't going to cooperate. The engineers had to learn how to work with it. And before they could build a road through the Tianshan Range, they first had to survive the mountain fighting back. A tunnel boring machine makes excavation look simple. The cutter head turns. Rock breaks. The machine moves forward. But underground, every meter can tell a different story. The Tianshan Shengli Tunnel was built through some of the most complicated geology along the route. And one of the most dangerous examples was a fault zone known as F7. As the excavation approached the zone, the geological conditions became much more difficult. There was fractured rock. There was the possibility of water and mud inflow. There was collapse risk. And there was a problem no tunnel engineer wants to hear. The TBM itself could become trapped. This was not a machine operating in a factory. If something went wrong underground, the mountain wasn't going to give the machine back easily. So the construction team had to adapt the excavation strategy to what they were actually finding underground. That is the part of tunnel engineering that is easy to miss from the surface. The plan is drawn before construction begins. The mountain gets the final vote. Every few meters, engineers need answers. Is the rock stable? Is water approaching? Is the tunnel deforming? How much pressure is being transferred into the surrounding rock? And what kind of support does this section require? The deeper the excavation goes, the more important those questions become. At the deepest point, the tunnel reaches a maximum burial depth of about 1,112.2 meters. That doesn't mean the road is more than a kilometer below sea level. It means that in that location, more than a kilometer of mountain sits above the tunnel. All of that rock contributes to the underground stress environment. And when engineers remove rock, those forces have to redistribute around the new opening. That is why excavation and support have to work together. Remove the rock. Understand the conditions. Stabilize the surrounding ground. Then move forward. The project combined drilling and blasting in the two main tunnels with TBM excavation in the central service tunnel. The service tunnel was crucial because it allowed crews to create additional working fronts for the main tunnels. Instead of a 22-kilometer tunnel being attacked from only two directions, the underground system could be divided into multiple sections. The project team called this approach long tunnel, short excavation, using the central tunnel and cross passages to turn one huge job into many smaller ones. According to Chinese transport authorities, the approach helped reduce the construction period dramatically compared with a conventional two-ended excavation strategy. But there was another challenge. Altitude. The tunnel sits in a region where parts of the route are more than 3,000 meters above sea level. The air is thinner. The temperatures can be brutally low. And construction equipment still has to operate reliably. One of the vertical shafts was excavated to roughly 706 meters, creating a direct connection between the mountain surface and the deep underground construction zone. Imagine lowering workers, equipment and materials hundreds of meters into the mountain, then doing it again, while the actual tunnel excavation continues somewhere below. This is why the four shafts were more than holes in the ground. They were lifelines. They helped with access. They helped with ventilation. They helped divide the enormous underground project into manageable sections. And the central tunnel provided another critical advantage. It gave engineers a way to approach the main tunnels from the inside. The result was a construction system that looked less like a single tunnel project, and more like a temporary underground network. But even with the right machines and the right layout, the mountain could still create surprises. During construction, crews encountered problems including collapses, mud bursts and water inflows. At one point, hard rock excavation equipment encountered extremely soft, unstable ground that could effectively immobilize the machine. The response wasn't to simply push harder. It was to change the method. That's the lesson the mountain kept teaching. The engineers weren't defeating the geology. They were responding to it. And eventually, after years of excavation, the two main tunnels finally met. On December 30, 2024, the breakthrough created a continuous 22.13-kilometer underground highway route. The mountain had been pierced. But there was still a problem. A breakthrough doesn't create a highway. Creates an opening. And now that opening had to become something people could safely drive through every day. This is where the most visible part of construction ended. And the least visible part began. The rock had been excavated. The tunnels were connected. But inside the mountain, almost everything that makes a modern highway work still had to be built. The road surface, lighting, power, drainage, ventilation, communications, fire protection, traffic monitoring, emergency response, and a way to move people and rescuers through the tunnel if something went wrong. The Central Service Tunnel now became especially important. The two main tunnels carry highway traffic. The Central Tunnel provides an additional service and emergency rescue route between them. That matters because inside a 22-kilometer tunnel, distance changes the meaning of an emergency. An accident several kilometers from the entrance isn't like an accident on an open road. There is no field beside the highway. No alternate road. No easy access from above. There is only the tunnel. So the tunnel has to contain the systems needed to manage itself. And one of the most important is ventilation. A 22-kilometer underground road needs controlled airflow. Vehicles produce exhaust. Fire can produce dangerous smoke. And in an emergency, where that smoke goes can determine whether people have enough time to escape. The 4 vertical shafts form part of the tunnel's ventilation strategy, creating vertical connections between the underground system and the surface. The shafts are effectively part of the tunnel's lungs. Fresh air can be moved through the system. Polluted air and smoke can be controlled. And the underground environment can be managed even when the mountain outside is freezing. Then comes fire safety. The goal isn't simply to extinguish a fire. First, people need to know that something has happened. They need warnings. Operators need to know where the incident is. Traffic has to be controlled. Ventilation has to respond. Emergency crews need a route to the scene. And drivers may need guidance toward a safe evacuation path. That is why the Finnish tunnel is not just a concrete structure. It is a coordinated system. And increasingly that system has a digital layer. Hundreds of high-definition cameras monitor traffic throughout the tunnel. According to Xinhua, the tunnel's digital twin system uses 740 panoramic and long-range high-definition cameras to help track vehicles and traffic conditions across the underground route. Instead of operators simply watching hundreds of separate screens, the system can build a digital picture of what is happening inside the tunnel. Vehicle stops. Traffic slows. An incident occurs. The system can help identify where it happened and give operators information they can use to coordinate the response. Then there is water. Groundwater doesn't disappear when construction ends. It still has to be collected and drained. The same is true for every other hidden system. Power has to remain available. Communications have to work. Emergency equipment has to remain accessible. Ventilation has to keep operating. And the road itself has to feel predictable. That last part is important, because when all of this engineering works correctly, the driver shouldn't notice it. They should see lanes, lights, concrete, and the road ahead. That is what successful infrastructure does. It takes an extraordinarily complicated system and makes the experience feel ordinary. The Tianshan Shengli Tunnel officially opened to traffic on December 26, 2025. At 22.13 kilometers, it became the world's longest expressway tunnel. The mountain crossing that once took several hours could now be completed in roughly 20 minutes through the tunnel. But that 20-minute journey is only the visible result. The real achievement is everything hidden around it. The support holding the mountain back. The ventilation moving air, the drainage controlling water, the cameras watching traffic, the emergency systems waiting for a problem that everyone hopes never happens. And beneath all of it, highway. Now the question changes. Not how did they build it? Why was building it worth all that effort? For thousands of years, the Tianshan Mountains were something transportation had to work around. Now there is another option. Go underneath. The new expressway connects northern and southern Xinjiang more directly, with the Tianshan Shengli Tunnel serving as its defining link. Before the route opened, traveling between Urumqi and Korla could take around 7 hours. The new connection cuts that journey to roughly 3 hours, according to Xinhua. The mountain crossing itself can now take about 20 minutes. For a tourist, that's an impressive number. For a truck driver, it means something much more practical. Fuel. Predictability. A truck carrying agricultural products doesn't care that the tunnel holds a world record. It cares whether the road gets the cargo where it needs to go. And that matters in Xinjiang because the distances are enormous. Cities, farms, and economic regions can be separated by vast stretches of difficult terrain. The new 324.7-kilometer expressway creates a more direct connection across the Tianshan barrier and links into China's wider highway network. There is also the weather. Mountain roads are exposed. Snow can close routes. Ice can make surfaces dangerous. Extreme cold can disrupt transportation. Inside the tunnel, those mountain conditions are no longer directly surrounding the driver. The snow can still be falling above. The wind can still be blowing outside. The mountain can still be more than a kilometer thick. But the vehicle is moving through a controlled environment. That is the real purpose of the project. Not the record. Not the photographs. Not even the tunnel itself. Connection. A faster connection between northern and southern Xinjiang. A more predictable route for vehicles. A highway that reduces the influence of one of the region's greatest natural barriers. And perhaps that is why the finished tunnel feels almost strangely ordinary. Think about what is above the driver's roof. More than a kilometer of mountain. 16 geological fault zones crossed during construction. Hundreds of meters of vertical shafts. Years of drilling, blasting, and machine excavation. Thousands of engineering decisions. Yet from inside the vehicle, most of that disappears. You simply drive. And that is the strange beauty of infrastructure. The more difficult something is to build, the less difficult it should feel to use. The driver doesn't need to understand the ground stress. They don't need to know where the fault zones are. They don't need to think about the TBMs. They don't need to see the ventilation calculations. They don't need to know how many people spent years underground making the road possible. They just need the road to work. And now it does. The Tianshan Shengli Tunnel is no longer a construction site. The machines are gone. The breakthrough is history. The workers have moved on to other projects. What remains is a functioning highway buried inside a mountain. And that brings the story back to the number from the beginning. 1,100 meters. That's not the length of the tunnel. It's not the height of a bridge. It's not the distance between two cities. Rock. A kilometer of mountain above a highway. And beneath all of that weight, ordinary traffic now moves through the Tianshan Range. That is the real achievement. The engineers didn't make the mountain disappear. They didn't flatten it. They didn't conquer it in the traditional sense. They learned how to work with it. They found the weak zones, measured the pressure, controlled the water, created access from above, cut the construction into multiple working fronts, and slowly turned a mountain into a route. The final product doesn't look like a battle with geology. Looks like a road. And maybe that's the best definition of successful engineering. The complexity stays behind the walls. What the world sees is movement. A truck carrying goods. A family crossing the mountains. A driver heading toward the other side. 20 minutes underground. Then daylight again. The Tianshan Mountains are still there. Just as enormous. Just as cold. Just as difficult. But they no longer have the final word over how people cross them. Because somewhere beneath more than a kilometer of rock, there is now a highway. And when you drive through it, you may see nothing extraordinary. Just asphalt, lights, concrete, and the road disappearing into darkness ahead. But above your roof is an entire mountain. And beneath that mountain is a road that took years to create. The mountain wasn't removed. It wasn't moved. It wasn't defeated. China simply found a way through it. And for the first time, crossing the heart of the Tianshan Mountains doesn't mean climbing over them. You can simply drive underneath.